This talk was about the food. We are thinking in the luxury, to have more, and that is not sustainable. We need to use what we have. It's all what you need to be happy and to be comfortable.
This is our composting facility, our organic waste recycling facility. It's a great way for cows to become more sustainable and getting closer to a zero waste cows.
Resilience is when life hits you really hard, that you get back up.
Resilience is bouncing back. It's about never give up and keep moving forward.
Hello there. Good evening. And we're very honored to have Professor Bill Sanders as the keynote speaker this evening. As an old acquaintance and a friend of mine, I'm really thrilled to be introducing Bill. I should tell you that Professor Sanders took the time to come here in presence. The only reason he didn't come is that he had to make this decision at the time we were all, very worried about what would happen with the recent pandemic evolution. So he wanted to know cows better, and we can only appreciate that. So Bill was the Dean of Carnegie Mellon since 2020, the College of Engineering. And actually, during 25 years before that, he was at Illinois, and he has had many roles in academic, teaching, leadership. He was director of the Discover Partners Institute, a research interface and translation institute. During 6 years, he was head of the ECE department. He was also director of two institutes, the Information Trust Institute and the Coordinated Science Lab. Amongst numerous awards, Bill is a fellow of the IEEE, is a fellow of the ACM, is a fellow of the AAAS. And he has published scientifically over 270 papers on security and dependability in the computing aspects, and also resilience assessment of critical infrastructures. More related to his forthcoming talk, he created some of the earliest secure power grid architectures and tools to assess grid architecture's resiliency. And as early as 2005, he was a principal investigator of a large NSF-funded project, which was the first ever university industry government partnership for power system cybersecurity. Some of the techniques he invented before were actually put in practice in those designs. So we're very much looking forward to your talk. Bill, the floor is yours. Thank you very much.
Well, thank you very much, Paulo. It's an honor to be invited to speak to all of you at KAUST today. And as you said, I would very much want to be there in person. It was only the global situation that kept me away. But I'm so glad we have this technology and that I can participate in actually multiple of the sessions today. And I enjoyed your talk earlier in the day. I'm going to give you a quick overview of really both the history of issues regarding power grid resiliency and really some of the challenges going forward. And then I'm hopeful that we can have a really engaging discussion about it. So we can start, if I can get, we can start by saying, what is the real challenge at the highest level? And as you said so well, the challenge is really providing trustworthy operation and trustworthy operation through resiliency. And we'll talk about that throughout this talk. So what do we mean by trustworthy? In the context of the grid, but really many cyber systems, it's a system that does what it's supposed to do and nothing more. And it's really important that you prescribe that it does not do bad things as well as do the things it's intended to do. And this is a really broad concept, a concept that encompasses safety, availability, integrity, confidentiality, performance, and really most of the abilities that that when we design systems as engineers, we expect them to have. It must do that regardless of the environment that it's in. And so we talk about broadly that there can be many impairments to trustworthy operation, and those can be accidental, as you pointed out in your keynote talk. Those can be due to design flaws, or they can be due to malicious attacks. And we'll focus a bit more on malicious attacks in this talk, but we will note that a lot of the techniques that are developed for malicious attacks also can be helpful for accidental failures and sometimes even for design flaws. And clearly, when we think about physical systems like the electric power grid, we have to be cognizant that they're cyber physical, that we have to make the whole system trustworthy, including both physical and cyber components and their interaction, not just the cyber part, not just the physical part. And I tell you that that can both make things easier. We can leverage the fact that there's physics associated with the physical systems, and it can make things more complex as well. So these are two things we can think about. So let me tell you a little bit of background just to get started. So this is a slide that comes from the Department of Energy in the United States, someone named Carol Hawk, who was my program manager for many years. And she said it so well that energy sector cybersecurity, and more broadly, energy sector cyber resilience, is not the same in energy delivery systems than it is in business systems. There are a whole set of reasons, and I won't take time to go through these slides, and I'd be happy to share them with you later. But basically, we need to invent new techniques that can be inspired by IT systems, cybersecurity, but we need to invent new techniques for the power grid. And you see a whole host of reasons here why that might be the case. There's no chance for downtime. There's a strong mix of legacy and modernized components. And those legacy components in most parts of the world are not going away from some time. There may be constraints on the computing resources. They're geographically distributed. They may be in places where power is not easy to obtain. And real-time behavior is very needed. So in many ways, we can be inspired by cybersecurity and more general cyber resiliency research, but we need to think very specifically about the context of the system that we are in. So let me give you just a primer, and for those of you who are power system engineers, my apologies, and for others to help you feel, classically, a power system is organized hierarchically. There are control areas. There are many control areas that may be overseen and controlled by a coordinator in different geographical areas. In the United States, there's a market that's a free market in which energy is bought and sold. There's an operator for that market, and there's a real connection to very broad areas. And so this leads to many, many challenges as we think about cyber resiliency for the power grid. The first is that we need to create a secure, reliable, and even perhaps at this level, resilient computing base. This ranges from the individual sensors that might be out on the lines and the wires that deliver the power, to the control centers, to the regional centers, and so forth going up. We need to support a large number of these devices that can be heterogeneous. There can be timeliness requirements, and there can be required communication between those devices. When we go up to the highest level, we may have very different regions of control. There may be business entities that are providing power to different geographical areas, and those different geographical areas may share or not share information freely with one another. And there may be regulatory limits of what can be shared, particularly in places where the operation and the business aspects of the grid need to be kept separate. And then finally, there's a whole set of cross-cutting areas that we need to deal with. There's a large, rapid propagation of effects. Generally speaking, energy cannot be stored to any large extent. So if there's a problem with the delivery of that power, it will be seen rather quickly. There's a need to adapt and adapt quite quickly, not on the speed of adaptation within a single computer, but in the speed of minutes in which these impairments or these problems can propagate throughout a very large system. And there's need to have confidence in the trustworthiness of the resulting approach. And this is a particular interest of mine, and I'll come back to that at the end of the talk. And this is all just complicated when we think about what now for about 15 years has been called the smart grid. The smart grid has all the challenges of the classical grid, but it has many, many control loops, many different entities, as you see on this slide. And one must think about that system and how the different pieces interact with one another. And this is one of many archetypical architectures for the smart grid. This one developed by NIST in the United States. So let me give you a bit of history just to start. The story begins in the United States anyway around the year 2000, where people were just beginning to realize that the cyber infrastructure of the power could be at risk. In fact, many people didn't realize at that time, and I have to tell you, I was working in that time on it, and it was very challenging to convince people that this is a real risk. There was a rapid advance to what I would call adolescence of the grid, and in fact, in some sense, I think we're stuck in this adolescent stage. So let me go way back, and this is a story from 1993. And the story there is one that was reported in a local newspaper in a state called Wisconsin in the United States, in a place called Milwaukee. And I just want to point out to you that attacks may be very low tech and they may be physical. The story that was reported in this newspaper article was the story of a J.D. Canapola, who you see there. It seems to be known also as Dr. Chaos. And what Dr. Chaos or JD would do is that he would go to bars and he would meet young people in bars. He would talk to them, hey, do you want to cause a power outage? And he would go and he in the back of his pickup truck would have spools of barbed wire, some metal that would be used to build a metal fence. And he would go out to where the control centers were, and he and his friends, after they had been drinking a bit, would throw these bales of metal barbed wire onto the power stations, causing shorts to occur, causing power outages to occur. So there's very low-tech ways, and in fact, combinations of low-tech ways and high-tech ways, when used together, may be the most effective and most challenging to build resiliency against. So there's a whole set of attack strategies that one might use. And as Professor Verissimo said earlier today, we have to learn to be attackers, or at least understand attackers to be defenders. And we won't focus on this today. But there are all sorts of different ways you might do this. One of the main ways would be to change the settings on breakers that keep the system safe, that cause them to trip, like the circuit breakers in your house, that cause lines to go offline, that cause too much current to then flow on other lines, causing additional breaks, and then what's called cascading failure. And so there's on these bullets, there's just some ways you might cause those things to happen. And as I said earlier, one of the main challenges is when you build combined physical and cyber attacks, that maybe a cyber attack will happen in a power station. For example, a rifle might be shot at a transformer to cause a local outage, thus causing people to focus their attention on that. And then maybe in the background, some of these cyber things would be done. So we have to think very broadly when we think about the impairments and the kind of attacks that might happen on the grid. So this problem has been worked on for some time. And in fact, in 2005, in the United States, to use just one example, the Congress created something called the Energy Policy Act. And the Energy Policy Act created a new organization, the so-called Electric Reliability Organization, or ERO. And the ERO was mandated to develop and enforce cybersecurity standards for the grid. A federal agency called FERC, the Federal Energy Regulatory Commission, appointed a private firm, NERC, to be the one that was in charge of those standards in the US. And in fact, over the next few years, as you see here, the standards first approved in 2008, and they've continued to evolve. The good news is they put mandatory standards on some aspects of cybersecurity in the grid, and they have imposed real penalties for not adhering to those standards. And here's just an example, and the violations of these standards are made public in the US. This is an old one in which a company, electric delivery company called the Reliability First Corporation, was given a penalty of on the order of $1 million US for lack of compliance with cybersecurity standards. Now, just because there's a lack of compliance with a standard or there is compliance with a standard does not ensure that a grid is resilient or it's cyber secure. And we'll talk more about that later. I just want to point you to a much more recent report that I participated in the writing of from the US National Academy of Engineering in 2017, called Enhancing the Resilience of the Nation's Electric System. And so in this report, about 200 pages in length, you can read in detail recommendations on how to make power grids more resilient. And I heard at the beginning, before my introduction, that there were people from KAUST there who gave their interpretations of what resiliency meant to them. And this book delivers a very clear description of what resiliency is with respect to the context of the power grid. There are two other documents I want to call your attention to. One, in particular, the one on the left-hand side of this screen called Communications, Cyber Resilience and the Future of the U.S. Power System, was a report from a workshop that I also participated in and helped organize, in which they're very recent. This is from 2019 or 2020, talking about some of the issues with making the power grid resilient. So let me quickly turn, and I'm going to move very quickly on this part, to some of the challenges that we see, some of the trends, and some of the gaps. I'm going to give you then two examples of research to address these challenges and gaps, and then we'll hopefully have a good discussion. So these challenges and gaps come from a white paper that my group at the University of Illinois wrote, and we'd be happy to send you, that was entitled From Security to Resiliency, Opportunities and Challenges for Smart Grid Cyber Infrastructure. So I'm going to very quickly go through these just to give you a feel of some of the things you should be thinking of if you want to do research and work in this area. The first is that the grid is transforming very rapidly. For several decades, there was very little innovation in power grid and its cyber infrastructure. But I have to say, in the last 10 to 15 years, there's been dramatic transformation. Dramatic transformation in the United States, but dramatic transformation all over the world. In Carnegie Mellon, we have a campus in Africa, and we do this kind of work in Africa. And particularly in places where the grid is not so well developed, there could be very quick innovation. That innovation, of course, can make things better, can make things more efficient, but it can also lead to very large challenges. And here are just some of the challenges. The fact that smart meters are pervasive now. The fact that there are many, many intelligent devices, each maybe that has passwords, each that might be secure or insecure in the substation in the field. The fact that there's an evolution to very large wide area measurement systems that can provide more data, but that data can be overwhelming. And the fact in all of this, as the grid is changing so quickly, the grid has many older components, particularly in countries that are more developed, that cannot support the modern security mechanisms that we want to try to provide. Going even farther, we're moving from the traditional architecture that I talked about earlier to the so-called energy Internet of Things and utility clouds. In fact, the management of grids may be outsourced altogether. I know of companies in Singapore that manage grids in China and Africa totally remotely, done through a cloud infrastructure. And you can only imagine the security and resiliency challenges that might come with that. Of course, the introduction of renewables, as is being talked about in other parts of this conference, is a key thing. Renewables can be very helpful in adding resiliency. This is diversity of another source of energy, but they also can be bursty in the ways in which they deliver their power. The wind doesn't blow everywhere all the time. The sun doesn't shine everywhere all the time. And these variants in these energy sources makes them challenging to use as the base power source for a grid. Electric vehicles, of course, are becoming pervasive, and electric vehicles can put a demand on a grid, particularly legacy grids that is maybe is hard to sustain. And then even more interesting from a technical point of view is that there's a large cyber infrastructure to support the charging of these vehicles, and it itself may not be resilient. There are two challenges I want to talk about, broad challenge. One is that there's a very complex interaction between physical grid resiliency and cyber grid resiliency. So very detailed and fine-grained and subtle things that go wrong on the cyber side could affect the physical side, and the other way around if sensors don't work. And so we need to understand that interaction between the cyber and the physical side of the grid. And then the grid itself is dependent on other infrastructures. The grid may require, for example, the production of energy may require natural gas or other forms of raw material to function. And so the interaction between the grid itself and other critical infrastructures also could have an important impact on grid resilience. And then finally, I want to quickly talk about a couple of gaps. The first one is that in this new world that we're imagining and we're building as engineers today or inventing as engineers today, we have a gap in the sensing, the analytics, and control that would be needed. We need to rethink the hierarchical control of today into much more distributed control. We need to understand how to best use the extensive sensing capabilities we have. And we need to use things, it's fashionable to say AI today, but we need to use data analytics to understand the data that we're collecting and to do better control. And you can imagine there could be attacks on these control algorithms themselves in a way that you could provide them bad data in which wrong decisions that are made to dynamically adapt the grid, just like a data attack on an autonomous vehicle could make it decide, as we heard in an earlier talk today, make it decide to drive in an incorrect way. So there's real issues as we build this sensing, analytics, and control infrastructure that it itself needs to be made resilient. We need to build, and in the last slide I was talking about the cyber infrastructure to manage the grid itself. We need an underlying mechanism to detect and respond to cyber attacks that may occur and physical attacks that may occur. There's a profusion of potential attack points, a very large and complicated and distributed attack surface. We need to think about how we can use the traffic on the grid itself to do some of this detection. We need to understand how both the physical and cyber state together can be used to recognize attacks and respond to attacks. One of the challenge, of course, is that there can be too much data, or what people today are calling a data avalanche. And then on the side of the response, we need to carefully consider the consequence of the response. Just shutting down to a safe state is not an option, as it might be with a classical IT system. And we ultimately have to operate through cyber attack or failure and push forward to a new good state rather than fall back to a safe state that may not deliver the service that the grid needs to deliver. So a whole bunch of challenges on the detection response side. Another large challenge, and I'm going to focus on this in the last part of my talk, is resiliency assessment itself. We can't just build this new grid and hope it will be resilient. We have to both monitor its resiliency in real time. We have to detect if there are risks to resiliency. And we have to design it, as engineers, we have to design it using principles where we can make design choices based on the resiliency of the resulting designs. So both at design phase and at operation phase, we need to have extensive techniques for resiliency assessment. And there's a rich set of, as Professor Verissimo knows, there's a rich set of techniques available for a dependability assessment, reliability and availability assessment to accidental failures. But this is a much more complicated business when one has malicious attacks. And then finally, we need to address both technical and non-technical issues. We have to recognize that the components that we're going to deploy in the grid will last for a decade or more, right? That's the business model that requires that. They're not like our cell phones that every 2 or 3 years we can get a new cell phone. And we have to understand, as was pointed out in some of the answers to questions earlier today, that there are social, cultural, and human factors that have a large impact on the overall resiliency of the grid. Humans are in the loop and part of the loop of this system, and we need to understand how those humans interacting with the system both help and harm its overall resiliency. So I'm going to close by talking about a couple of approaches to addressing these challenges at a high level. And these approaches come from a long series of large centers that I was involved in the leadership of. And the most recent one is called CREDC. You could look up the website online here. It was about a $30 million US initiative. The primary leader of that initiative was the Information Trust Institute at the University of Illinois, an institute that I founded and operated. And myself, David Nickel, and Pete Sauer were the co-PIs of that center, in which we led a team of 11 universities and US national laboratories, and about 30 or 40 people together with a team of about 100 companies that were looking at the issues and challenges and solutions to the resiliency of the power grid. I think I'll skip the goals in the interest of giving you a couple examples, but suffice it to say that we took a very practical approach. We used sound academic research, but we weren't satisfied with just publishing a paper. We wanted to get that research in the field and have it make a difference. So the first example I want to tell you about is risk assessment of energy delivery system technology and systems in the field. And I'll take you back to something I showed earlier, in which I said there were large penalties for misconfigurations of the networks and the firewalls that run the overall grid itself. And in fact, as I said, NERC and FERC specify certain configurations of those networks. And if auditors detect that you are out of configuration, then you'll receive a daily penalty that can be quite high, as you see here. And so the question really is how, both statically by investigating the firewall configuration rules and dynamically by monitoring actively or online, in an online way, verifying those configurations, can we ensure that there aren't vulnerabilities in the network that has to run the grid due to firewall misconfigurations? And what I want to tell you just briefly about is a tool called NPView. NP stands for Network Perception. We'll get to that in a minute. But the NP tool is a tool developed as part of this CREDC research program that performs a comprehensive security policy analysis of the computer networks, or the so-called OT networks, operation technology networks that run the grid itself. And it automates most of the reporting process required during an audit that is now required by law of these networks that run power grids in the United States. And what we developed first in an academic setting and then later in a commercial setting was a comprehensive tool that used model checking techniques. So the tool took as input the firewall configuration, the rules themselves. So you could download these firewall configuration tools, and you could see here's a power grid network infrastructure that has a set of firewalls. I see 6 different firewalls, but large networks can have 50 or 100 or 200 or 500 firewalls in them. It takes all these local policy configuration rules, it creates a global map, and it tells you if there are any misconfigurations in the individual firewalls that can lead to global problems of the cybersecurity and the resiliency of the overall network. And it can provide you with points where you have the most risk, and it can tell you how to fix those misconfigurations in order to make the grid itself, or the infrastructure itself, both compliance with the law, so you won't get these penalties, and more cyber resilient. And this tool was developed in an academic setting, but it's now become a commercial product. And there are several hundred electric utilities that now use this tool to manage the cyber resiliency of their grids themselves. I should say that the primary focus of this tool right now is exactly what we're talking about today, electric power grids, cyber resilience. But the tool is also starting to be used in the oil and gas industry, and in fact used in the credit card processing industry itself to ensure the resiliency of those credit card processing devices that are in almost every shop today. So this is an example of how something that began as an academic dream has gone all the way to the commercial setting, and is a thriving small company now in the United States. The second example I want to show you is about design time cyber resiliency assessment. And again, I'll just give you the flavor of this in the next few minutes and then open it up to questions and discover. So while the first example showed you that you can be very specific and you can take things from the configuration of the system to determine its resiliency and in fact how to make it more resilient. The second issue is when I'm designing a new cyber infrastructure, whether that be for a grid or an autonomous vehicle or any other nation critical cyber infrastructure. You have to make decisions about how to design that resiliency in from the beginning. And what this tool that we've developed does uses something that are akin to attack graphs, but much richer, that look at different possible ways in which an infrastructure might be compromised. So this is called an attack execution graph. This is an attack execution graph for the distribution side of a power grid, the part of a power grid infrastructure that would deliver electricity in a single city. And these yellow attack bars are called attack steps, and those attack steps are ways that the attackers might get to the goals. The goals are the orange ovals on the bottom. And the question really is how vulnerable is this design, and how could I change the design to make it more resilient? And so in the tool, you both specify an attack execution graph, and you specify different kinds of potential attackers and what their goals are. The goal of everyone from an engineer inside the company who may want to sabotage the grid to a government level attacker. We developed a tool called Advise that will advise you on how to make designs more resilient, taking both system information and adversary information. The tool generates things akin to simulations that then get executed, but they're simulations that have some aspects of game theory built in. And the game theory plays the role of the attacker because the attacker himself or herself will be very adaptive and do the thing that makes the most sense. We built a tool in which you can specify these attack graphs. You can specify different kinds of adversaries. You see this adversary has certain skills. Adversary has an initial starting point, just like in a red team experiment. And the attacker has some goals that they want to try to achieve. And what the tool can do is perform an analysis using one of these specialized simulations that I talked about that can tell you what the preferred attack path will be for different kinds of adversaries. And you can see here that 3 out of the 5 adversaries in this case will try to alter the protection settings on certain devices in the network. And that tells you then that you should work to reinforce that portion of the system. So it tells you where the weakest link is, and it gives you ideas on how to fix that weak link. And what this shows you is, depending on the design of the system, those attack paths may be very different. There's something called recloser radios that will reclose switches in a distribution network. And if you don't have that innovation, that thing that could make the network supposedly more resilient, because when a failure occurs, it can change the path of electricity, the attacker will attack in one way. And when you do, you see that the attackers may focus their attention on a different technology. So this shows that when we build in new features in a system, we need to understand that attackers may adapt how they the attack. The tool also allows you to look at resiliency in an absolute sense. Now, we don't really believe these numbers are precisely correct, but we can look at things like time to achieve attack goals, and we can look at, in a relative sense, for different designs, two designs here, one with recloser radios, one without, how long it would take attackers to reach the goals that they have. So let me close with some final thoughts. The power grid has evolved greatly in the last 20 years. It's an incredible opportunity for academics to work together with industry to apply fairly sophisticated algorithms and analysis, including AI-based analysis. And it's a system in which, while to make it perfectly resilient may be impossible in the short term, that we can make significant progress by working on parts of the problem at a time. I think we need to think about how to design resiliency in from the beginning, that we must break out of the current Pearson patch mentality. What I mean by that is that in many cases now we wait to see what attackers do and we patch that, and then attackers move to a new place, just like we saw in that last analysis I did. So we need to design resiliency in from the beginning. We need to think both in the short term and the long term at the same time. And what I mean by that is that there are urgent problems. We need to make changes today, but we can't let the fact that we keep making these short-term changes not allow us to think architecturally and start to architect that new grid, particularly in parts of the world where we have a chance to reinvent how we deliver electric power. I think it's very key that academia, industry, and government work together to do this. We haven't talked about this, but in most countries, the way in which the power grid run is very complex from a policy point of view. And understanding and driving technology through government policy is something that's particularly important with this technology. And I think these groups need to work together to make progress. So thank you for your attention. I hope this was interesting. I'll now take my slides down and turn it back to you, Professor Verissimo, and open the floor for questions.
Thank you very much, Bill. So, while you guys get prepped to ask some questions, please feel free to get near the microphone. There's a couple of them. There are some questions online as well, so I'll start with the online questions. So, Bill, there's an interesting question. Actually, I'm also interested to know your opinion about how much of these cybersecurity and dependability and resilience techniques that have been around, how much of that, even some of those that you have explained, are expandable to other sectors, other utilities like water distribution or even, industrial control?
Oh, it's a great question, Paulo. So you saw me argue at the beginning that one size doesn't fit all, that cybersecurity and cyber resilient for the power grid is not the same as cybersecurity and cyber resilient for general IT systems. I firmly believe that the best solutions are solutions that take into account the physicality and the physics, if you will, of the cyber physical system that you're trying to make cyber resilient, and use those characteristics to invent and refine algorithms to make them better. Having said that, there's a whole set of critical infrastructures in which there are similarities. So the approaches that are invented, particularly the cyber resiliency approaches that are invented, will differ in some ways for different infrastructures. But there's a lot to be learned from one that can be applied in the next. And so I think this requires a change in mindset. I know a change in mindset that you agree with. in which we start from the system. We don't, a classical computer scientist may think of everything as an application for some algorithm or some approach. Well, I prefer to think in the opposite direction as an engineer. I'm trained as a computer scientist, but I start from the system and the problem. And then I invent solutions that are based on these sound techniques, but that respect and take into account the characteristics of the system. But clearly, once you adopt that approach, there's a lot of similarities between systems that can be leveraged. So that's a high-level answer, and I'd be, we're working in the oil and gas industry as well now, and starting to work in some other critical infrastructures as well.
Very well, very well. And actually, there's a somewhat related question, but intra-sector. So there's a question saying, what about, so are there cybersecurity standards that, in the US or even elsewhere, that do they focus only on the more classic, grid systems, or do they already encompass for cybersecurity the prosumers, so distributed generation and the likes?
Yeah, so the cybersecurity requirements that I am aware of, for example, the NERC CIP ones in the US, and there are similar ones in the European Union, and I'm not as familiar with the rest of the world. Those are really about cybersecurity compliance. And I don't want to be too negative, but you can comply in a way that doesn't lead to better resiliency or doesn't lead to better security, cybersecurity in a system. So they're a great start. They've made progress. They've evolved a lot in the 15 to 20 years that they've existed, but they still put too much focus on individual components and whether they are secure or not. First, as opposed to overall system approaches, and in cyber resiliency, we know it's not about individual systems, it's about the system architecture. And second, they are not cognizant of the fact that the different critical infrastructures, say that oil and gas is interrelated with power. If you don't have power, you can't deliver the oil and gas. If you don't have oil and gas, you can't deliver power. And that's just a very simple example. And so it's a green field there. I think there needs to be much more thinking both at the system level, within the power grid infrastructure, and across infrastructures. We're a lot better off than when we started in 2000, where I started the talk. And we're a lot better off even than where we were in 2010, but we still have a long ways to go.
Yeah, I don't resist repeating your quote, which we agree and we teach about it. Compliance or maturity is not security or dependability. It helps, exactly. But it's not that. Yes, absolutely. This is confounded. All right, so there's a very interesting question, which is more of a techno-philosophical term, but I would like to hear your opinion about that. And with the evolution of the systems, and of course we talked about prosumers and things, so the grid is also always evolving, and so the threat landscape is also evolving. So we have been, always one step behind, so to speak. And the question is, do you believe that whatever techniques we think about, do you believe we will ever be one step ahead of the attackers?
Well, we'll never be one step ahead. And I heard your opinion about this earlier today. My opinion is we'll never be one step ahead if we continue with this Pearson patch mentality that I talked about at the end, if we just find problems and fix them. And even more so if we only think about the short term. I think I'm an optimist by nature, and I think there is a path to maybe not perfection, but something much better than perfection and getting ahead by designing in to architectures in a very different way. Now, the real challenge with that is that this is one of the most expensive infrastructures in the world. And there's a huge amount of legacy equipment and process and personnel invested in what we have today. And so we can't just throw it all out and say, okay, we're going to invent a better one. And so it's extremely complicated to chart a path from here to there. But that doesn't mean we shouldn't think about it. And it absolutely means we should make sure we don't just always think about the short term and patching the problems we see. So will we make it or not to that nirvana? I don't know. But we surely need to invest a certain fraction of our effort in that direction, even if it takes a long time. So that's my thinking on this.
Thank you. So that's another question that I like very much. You know, like you, we had teams trying to learn how the attackers, what is the attacker's mind, and learning their techniques. And we also did analysis that found concrete attacks. So the question is, from your experience, what were, you know, the most surprising or challenging or sophisticated concrete threats and attacks that you have seen? Those you can talk about.
Question. Yeah, good question. I mean, you know, you mentioned Stuxnet earlier in the day. I can imagine, particularly with the power grid, the attacks on the power grid in Ukraine is the most widely seen, complicated, and I chose not to take time to talk about that attack, but there's a whole talk that we could give about that. There's a lot known and publicly known about that. And once again, it was a very complex attack that had physical components, had cyber components, had attacks on the telecommunications system that stopped communication, that hampered the recovery. You know, the most interesting attacks, the most complex attacks, the ones that we're all most afraid of, are these ones that are multi-step and involve, you know, multiple diverse weak links in the system. And, you know, the Solar Winds attack, most recently in the US, there are plenty of public examples here. So, you know, when we started working in this area almost two decades ago now, there weren't so many examples of these, and what we did know wasn't so public. I'm sure there are plenty of things that aren't public, but there are plenty of things that are public now, providing you know, a rich basis for academics to think about how to innovate in this space. So, hope that's helpful.
Absolutely, thank you. So there's an interesting question that perhaps would help, for example, here in the Kingdom to replicate some of the initiatives you took. The question is, what were the primary success factors to achieving such a large and collaborative consortium with key players from academia, industry, and government all participating? And referring to the experience.
Great question. Well, like I told you, I'm sorry that I'm not sitting with you in the Kingdom today, and I'd have a better perspective once I came and visited, because clearly, maybe I'll start by saying that the way in which power grid is managed varies greatly in different parts of the world. I've done some work on the Singapore grid, and it's very different than the US grid, and as you and I both know, and in the European Union, there's another very different model, and so forth. So on one way, the technical details will vary. Having said that, you know, I think it requires, we all know that the diversity of people lead to solutions that are better and stronger. And in this case, by diversity, there are many, of course, many ways in which diversity, many kinds of diversity that help us. But in this case, the diversity of thought between policymakers and government, between operators, which may or may not be the government, but the people that have the perspective of operating the grid, and then, so the operators, the vendors who make the technologies, and the academics who can think out of the box and can innovate together with those people. One of my sponsors used to say to me as we were managing these large projects, that you should engage early and you should engage often. And so we would get together very frequently with those different groups I talked about, and we would brainstorm together. And then us academics would go back and work on things. That example of NPView and the tool that's now a commercial tool, that became viable because we had an academic idea that then we convinced one of our industry collaborators, in this case Ameren, a large electric power company in the Midwest portion of the US, to try that tool out. They tried that tool out, and the government auditors were amazed at what it could do. They started using it, that then drove other energy companies to use it, and then ultimately the tool was commercialized. So I think by getting these very diverse groups, government, operators, vendors and builders of the equipment, academics together early and facilitating that, this is really the key to success.
Thank you. Okay, so I think I've earned the right to ask you one question of mine, and that's going to be the last question of this session. And so considering the broad set of fault and intrusion tolerance techniques, which I believe are the starting body of this fusion between security and dependability, and anything from masking, and BFT, which is costly, to detection, recovery, reconfiguration, moving target defense, where would you see the body of knowledge from AI, ML best put to use to help improve those techniques to withstand, the more sophisticated threats?
Well, Paulo, that's a trick question, because I believe...
What would you expect from me, right?
Yeah, right. I believe deeply that there are many, many places, right? There are many, many places, and it really goes back to what I said earlier, that what I like so much, I like so much working in this field because I think we're making the world a better place and a safer place by doing so. But I like working in this field also because it's not all or nothing. That, whether we use AI techniques to forecast weather so we can better exploit renewables, or we use AI techniques to detect a certain attacker in a combined physical and cyber state of the system. And I could go on and on. So there are so many places, and I think it's up to the ingenuity of the many people that are now working in this field to say, I can apply it here and I can apply it there. And as I said before, it's not just bolting it on, it's adapting. We all know that, that deep learning techniques on their own are not a panacea. So we're going to have to adapt these techniques, but they can be adapted in many, many places for many uses. So there's not one, and I can't give you an exhaustive list that just says the future is very bright. But I'll close by saying we really need to understand the systems, right? There's another saying that I like very much, that a fool with a tool is still a fool. And that says that if we as humans don't understand those AI techniques we want to apply, we won't get anywhere with them. So thank you, Paulo, and thank you to the audience. I wish I could have been there with you in person, but it's been a real pleasure to interact with you in this way. And I look forward to the day we can meet in person.
Bill, it was a great pleasure, and yes, that day will come, definitely. Let's give a hand to Bill. Thank you very much, Bill. Take care. Thank you, ladies and gentlemen. We've closed the session.